And you heard probably Polly saying, yeah, TCP increases the window size when there are no losses and decrease when there's a loss. But if you think a little bit carefully, in TCP, the sender detects a packet loss two ways. One is, yeah, there's a timer set when the packet is sent. When the timer expires, the sender there discovers the packet is lost and then retransmit. But in TCP, there's something also called fast retransmission. We are retransmitting packet faster right after receiving triple duplicate X. So there are two ways in TCP sender to detect a packet loss. In fact, in TCP's congestion control, we are also adjusting the window size differently depending on which type of loss is being detected. First is a loss being detected by sensing the timer timeout. We then set the window size all the way down to one segment, okay, and then grow exponentially just like in slow start state. After a certain threshold, then grow linearly just like in the congestion avoidance state. On the other hand, when the loss is detected by seeing 3 duplicate acts, then the congestion window is actually cut to only half the current window size, not all the way down to 1. And then grows simply linearly. So this is very much like what? AIMD. Yeah, you're actually right. When the loss is detected this way, the TCP sender is actually dropping the sending rate to half and then continue on with the AIMD, therefore, into the CA state, the congestion avoidance state. So the TCP connection here is still in the steady state. But if the loss is detected this way, it appears that the TCP thinks this is actually a more serious scenario. Therefore, the window size needs to go all the way down and then being reinitialized, okay, until the window size grows to a certain degree. Then we do the AIMD, like in the steady state. Okay. Now, based on your intuition, which loss of these two you think is more serious? Yeah, I know, it's quite obvious, right? Because in this case here below, at least you get to receive 3 duplicate acts. That indicates the network is still capable of sending 3 packets through. Therefore, you get 3 acts back. But this scenario here, at the top, you don't get any data through, you don't get any data back, or you get only 2 duplicate acts back. So, yeah, more serious. Therefore, windows drop down even more aggressively, all the way down to 1, and that's restart, reinitialize again. Okay. Now, the only thing that you thought, interesting is this. So we have not yet defined what is this threshold yet, because it seems that this threshold is there to determine how a TCP connection there start from the initial state, entering the steady state. So that is also the point to decide when do we change the mechanism from slow start to congestion avoidance. First point to add to the slide is this. The threshold in TCP's implementation is called SS thresh. You guess, S and S here actually meant S and S here in slow start. Second point, the whole mechanism differentiating how we adjust the window size depending on the type of loss being detected is implemented in TCP Reno. Yeah, I know. TCP designers is a bit weird. They like to call different versions of TCP with names instead of using a number. So Reno there is essentially the version 4, TCP version 4. There's another version of TCP, TCP Tahoe. So this is actually the first generation. So What's being designed there is this. The loss, no matter whether it's detected by timeout or 3 duplicate acts, the window size is adjusted the same way, always down to 1. That means Tahoe there is very, very conservative. Whenever there is a loss detected, the sender always go down to the lowest rate possible. And that might be a bit too slow based on experience, therefore in the second generation. The designers begin to say, hey, maybe in this easier case, okay, at least we see 3 data go and then 3 duplicate acts back. It's not so bad. Let's only cut the window size to half and then remain in the congestion avoidance phase. So what I'm illustrating here is TCP Tahoe's window size changing over time. At the beginning, window size set to 1 segment. And then slow start, right? This is the initial phase. And therefore you see exponentially fast growth, a concave curve. And this is going to go until we hit the slow start threshold. That's when we exit slow start and enter congestion avoidance, where we do AIMD, so additive increase. At this point, we detect a packet loss due to 3 duplicate acts. But in Tahoe, we'll just drop the window size back down to 1 again. And then slow start again, a concave curve, until we hit the threshold again, and then AIMD again in the congestion avoidance state. Now, what's in Reno is, however, when we detect 3 duplicate acts, a packet loss, what we do is more simple, where we just reset the window size to half of the original window size, which is 12. So we set it to 6, and then continue to grow the window size AIMD, such as in the congestion avoidance state. Okay. Now, by looking at this plot, you also see, hey, we are switching from the slow start to the congestion avoidance state using the threshold. At the beginning, the SS thresh is initialized to a fixed value. But afterwards, you see the SS thresh is also changing. And when we detect a loss, when we need to reset the congestion window size down to some lower value. When that happens, when the packet loss is detected, the threshold here is also reset. And the value is set to exactly half of the window size before the packet loss is detected. So SS thresh is set to half of the window size just before the loss event. Okay. So in the TCP Reno's case, it's convenient. We set the threshold to the half of the window size, and we also set the window size to half of the earlier window size and continue to grow like this. So it's also saying passing the threshold and then this connection in the congestion avoidance state. If we go back to the original question asking, when do we switch from the slow start state to the congestion avoidance state, or from exponential increase back to linear increase? Answer is very clear. Yeah, once the congestion window hits the SS thresh, the slow start threshold. Because if you look at this, slow start, passing the thresh, growing linearly. Slow start, passing the threshold, growing linearly. And in this case, we see 3 duplicate acts, therefore we drop the window size to half, and we drop the SS thresh also to half. But hey, as long as it's beyond the thresh, the window size grows linearly, then the design does not conflict, okay, with other parts of TCP's congestion window adjustment mechanism. Now let's summarize TCP's congestion control. And what I'm going to show you is actually a little bit more formal using a finite state machine. And you see how TCP sender here implements, okay, the mechanism of adjusting the window size. The full finite state machine has 2 states, okay. Each represents, different phases of TCP's congestion control in a connection. So the first is the initial phase, the slow start phase. The initialization transition here is actually initializing the condition window size to 1 segment, and then initializing the SS thresh to 64 kilobytes. I think this number could differ from operating system to operating system, and then initializing the duplicate add count. Alright, so that was clear. Let's move to the normal transitions. There are 4 of them. If you look a bit closer, the top 2 here are actually the transitions handled in the cases where the sender receives X. The bottom 2 are the cases where the sender detects losses. So this one here is actually detecting a loss due to receiving 3 duplicate acts. This transition here is actually detecting a loss due to timeout. Now let's talk about each of these transitions a bit more. So number 1 here is if we receive a new ACK. Now according to source star mechanism, the congestion window needs to be incremented by 1 segment, and that's it. So duplicate ACK count is reduced to 0 just so to clear all the duplicate ACK counts, because now we are receiving a new ACK, so we should definitely clear the dup ACK count. And at this point, then we employ the rest of the sender's mechanism, the RDT part of it, so that we slide the window over and then send new segments. And how much we send out there depends on the result of the congestion control mechanism working. And next, transition number 2, this is when we receive a duplicate ACK. So what we do here, of course, increment the counter for duplicate ACK. And what do? The congestion control power says no more, right? Unless the count here reaches 3. That triggers transition 3. Okay. Now in RDT of TCP, this event is going to also trigger fast retransmission. So in a way, when there's dup ACK count equaling 3, then we do something for the congestion control and then some more for the reliable data transfer. Now in the congestion control, what we do is setting the SS thresh to half the window size, and window size to half of the current window size, which is now the value of SS thresh. And then reset the duplicate ACK count, right? And then we can begin doing the RDT, which is to fast retransmit packets. Now the number of packets we can send out then is determined by the congestion window size we just set aside earlier. Transition 4, this is also packet loss, but this is packet loss detected by having a timeout. So in this case, the congestion control says we need to set SS thresh to half of the window size, and the window size all the way down to 1 packet, and then reset the dup ACK count. And then from here, the RDT mechanism, which is what? To retransmit the missing segment. And because this time, in this case, the congestion window is set to 1 packet, therefore we only retransmit 1 segment. Okay? No matter how it is, how many packets have been sent, how many yellow packets or yellow bytes are there in the sliding window. Right? Done with the slow start state. Now, let's move to the congestion avoidance state. So the first thing is, hey, when do we transition from SS to CA? Yep, when the congestion window size is larger than the SS thresh. And that takes us to the congestion avoidance state, where we see again, transition new ACK, transition duplicate ACK, transition dup ACK count equal 3. And hey, where's the timeout state? Well, the timeout state is actually here, right? Because when we're in the congestion avoidance state, timeout is actually serious packet loss. We reset the congestion window down to 1 end. Start from the slow start, increment the window size exponentially, start from the slow start. So we need to do a state change in this finite state machine. going back from CA to SS. Okay. And otherwise, all these the same, just like timeout event. Similarly, for dupe egg count equaling 3, all the same, all the same. Okay. Actually, similarly for dupe egg, just incrementing the duplicate egg count. But the last one, the new egg, wow, we need to be careful here, all right? Because in SS versus CA, when we receive a new egg, meaning no loss, we actually increase the window size differently. So yes, this is why you see here. In SS, in SO star, we're incrementing the window size by 1 segment per egg. Here, we need to increase the window size by 1 segment per round trip time. So be very, very careful here. This is receiving an egg. Now, hey, checking and we see that there's 1 round trip time elapsed. So we need to figure out exactly the amount to increment to the window size so that after 1 round trip time, the increment will be exactly 1. And how do we do that? Think this. If the window size is CWND and the packet size is MSS, how many packets will be out in 1 round trip time? Yeah, this many, isn't it? Okay. And after all these packets come back in, the increment of the congestion window should be 1. That is saying we cannot be incrementing the window size by MSS. We need to increase this much. Okay? After this amount of packets received, then we add to this value. So we need to divide this value by these. That would say this is the amount we need to increment per packet. Okay? So if we rewrite this formula here, it's what? MSS multiply, so MSS multiply reverse of CWND to MSS. So after reversing, MSS at the top and then CWND at the bottom. And that is TCP Congestion Control Sender's finite state machine in a simplistic way. You see here, let me summarize again. Yeah, so these are the events receiving new egg. These are the events handling timeout. And these are the events handling receiving the duplicate eggs and it's reaching the count of 3. This finite state machine, now we walk through it. It's kind of symmetric and clean, relatively easy to track. This is also the mechanism implemented in the TCP Tahoe, the version 1. In TCP Reno, it's actually being extended. So the hack here is called the fast recovery. Okay. Now, this version looks substantially complicated, but okay, let me tell you this. Hopefully makes it a bit simpler for you. The only transitions that are actually touched from the previous finite state machine are just these. Okay, the case where the dupe egg count reaches 3. So previously what we do is this. We set the SS thresh to have the window size and the window size to SS thresh. But now, okay, in Reno, we actually add 3 more segments to the window size. So we are actually a little bit more generous about setting the window size. And the logic behind this is, hey, if we receive 3 duplicate eggs, that means the channel between the sender and receiver, there's enough capacity to allow 3 data segments to go. Although out of order, still triggering duplicate eggs to come back, right? So 3 spaces, therefore generating 3 duplicate eggs. So there's enough capacity, right? So we don't have to go all the way down, okay, or half down. So as long as, hey, we're seeing, duplicate eggs, that means the capacity is still there. Maybe this is just a very, short-term congestion, short-term pre-congestion, okay, happening. So maybe we just keep, pushing a little bit more, and when the short-term outage or short-term congestion goes out, then we can come back to normal. Okay, so this is the logic behind the fast recovery mechanism here. So after adding 3 more segments to the window size, we enter the fast recovery state. And stay in the fast recovery state, we apply the same logic. As long as we receive a duplicate act, we continue to increment the window size. Because being able to receive a duplicate act is because we allow one data to go out, right? Yeah. So this is going to be repeated until what? Until we finally get a new act back, or all these extra packets we send out by being more generous about the window size somehow get dropped in the middle, meaning the congestion is not short term. It's a bit more pathological, persistent. So we will run into timeout here. In this case, drop the window size to 1, feel free. But if it's in this case, it's okay. Then we can just reset the window size to normal, which is half of the window size, and then go back to the congestion avoidance state, and then begin linear increase again.